Alrighty, good morning, lads and ladies. Welcome back to Calc 2. Today is our last class meeting before exam 1. So I thought we would do a few things today. We can, of course, focus on solving some problems and trying to get you guys as comfy as we can for the test. And I also would like to kind of introduce a little bit of the material in the section we are heading towards. But my main focus today is to get you guys some more practice, to get you, like I said, as comfy as we can for the test. So kind of in the same spirit where we left off on Wednesday, I'd just like to solve some problems from section 7.5 or anything homework or study guides that you guys would like to talk about. Apologize for the slightly late start. My son is a bit sick, so we're all having a bit of a hard time getting appropriate amounts of sleep and all that stuff. So without further ado, turn on the dot cam, get moving. I did take a quick look at WebAssign this morning, and I see that there are some more extension requests in. I think I had 63 of those yesterday. So I'm doing my best to keep up with the requests as they come in. But if you've submitted one since yesterday afternoon, it probably has not been granted yet, but will be granted today. All right, here's the thing. Let's see. 2312, section number 004, which is Calc 2. Today's 9/24. Today, we're going to try to prepare a little bit for the test. Send questions. You can send those in the chat, right? So just into the chat, type, homework 5, problem 3, or study guide 1, problem 2, that sort of stuff. The other thing I'd like to do, introduce the concept of an improper integral. Which is section 7.8. That's the first section we're going to hit after we come back.
Is this gonna be on the test?
No, improper integrals very much not on the test. Not on this test. They're on the next test. So I'm not going to cover any of the deep material from this. Just want to kind of get you used to the idea. Plus a 50 for previous study guide. Was that intentional? Oh, no, Richard just pointed something out to me in the chat that there was some sort of, let's see, homework 5. Now, every time I make a homework set, I have to go in and change the number of answers you guys are allowed to use. And I was pretty sure that I set these to 50 for each one, but maybe on homework 5, it looks like I missed something there. Let's see. Yeah, let's do that. Okay. Yeah, so the input limit there should be updated now to 50 or 55, whatever that max is. Okay. So what would you guys like to look at? It's your day. Do we need a minute? I can give you guys a minute to look through the homework, study guides, maybe grab out your written work, see what sort of stuff you're getting into trouble with. See number 2 from the study guide. Let's keep these in. Let's try to get at least 4 or 5 problems here. well, from the first study guide, we want to see something like number 2. Let me see what's the real challenge in number 2 there. Oh, yeah, this ain't bad. Okay, so we'll do this one first. This one came to me as a DM. You see it's from section 6.2 here, which is nice. That allows us to infer a little bit the technique that we might want to use. But I'll set it up like we don't have a clue. So 8 sine x, 8 cos x from 0 to pi over 4 about the line y equals -1. Study guide 1, problem 2. And I'm going to have to change things a little bit. Find the volume, blah, 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 right? Obtained by rotating the region bounded by the curves. They had 8 cos x, 8 sine x. I'll keep the about y equals -1 and the 0 less than or equal to x less than or equal to pi over 4 part. I know people are going to have different randomly generated numbers though, right? There's only so much we can do to change this up. How about, yeah, there's really, just change the amplitude a little bit. Okay. So of course, the thing to do is to sketch the region, right? The region is between 3 cos x and 3 sine x from 0 to pi over 4. Sketch this axis of rotation, and then to draw on our little strip. Kind of once you've got that strip drawn in, we can think about it as rotating the strip. We'll call this 3. Then 3 cos x. Here, call this pi over 2. Cos x from 0 to pi over 2 looks something like this. Right, and continues over this way. And then 3 sine x. Here. This thing. So this is your curve, right? This is 1 equals 3 sine x. This is 1 equals 3 cos x. Definitely you gotta know what these curves look like to even get started here. Hopefully you know what sine and cosine look like. Multiplying by 3 or an 8 just stretches them vertically, right? Stretches their amplitude. And this is pi over 4 right here. The place where sine and cosine are equal. Might be the same place where 3 sine and 3 cosine are equal. Region. Region bounded by those curves from 0 to pi over 4 is this pencil shaded region. We'll call this right here y equals -1. That's what we're going to rotate about. So it might be a little hard to picture what the whole solid looks like. You get from taking this region and rotating it. It's definitely flat on the bottom. Definitely some sort of concave curved surface inside, some slightly convex curved surface outside. But thankfully, we don't need to picture the whole solid. We just need to worry about this strip. I can think of that solid as being made up of a bunch of little discs or washers, each one looking like what you get from just this strip. I'm drawing the strip in perpendicular to the axis of rotation because one, it's a 6.2 problem, which means we only have the disc washer method available. Two, because if I were to draw it in horizontally like this, I've got some real issues with those boundaries, right? Like it would be a different boundary curve up here than it would be down here. So at the very least, you'd have to split up the integral into two different pieces. It's much nicer to do this with the disc washer method. So there's my little strip. Its little thickness is a little dx thickness. And when we rotate just that strip, we'll get a shape something like this. And a thin little washer. Everybody on board so far? So we sketch the region, sketch the axis of rotation, and then draw in our little strip. If we imagine rotating just this little strip about this line, it would generate a solid that looks roughly like this. Right? It's like a disc, but with the middle punched out, or a washer shape. Think of your axis of rotation as coming through this. There's two little statistics we need about this washer. We need to know the little inner radius. And we need to know the big outer radius. All right, so that's the distance from like the gap to the axis of rotation and the far end of the washer to the axis of rotation. In this picture, the inner radius is this distance, right? The gap from the near end of the strip to the axis of rotation. And this would be that outer radius, the distance from the far end of the strip to the axis of rotation. So little r here is the vertical distance from this curve down to this axis of rotation, which is the y value here minus the y value here. The y value here along this curve is y equals 3 sine x. So the y value there is 3 sine x minus the y value down here, which is -1. So that's minus -1, which is +1. And for the larger radius, the distance from the far end of the strip to the axis of rotation, it's the y value up here minus the y value down here. So the y value up here, this is the curve y equals 3 cos x. So this is 3 cos x minus -1, which is +1. Okay, and the thickness of this washer is the thickness of that strip. It's a little dx thickness. Questions so far? This is most of the hard work done. So Kylie asked a good question. If the axis of rotation was y equals 1 up here, would r be 3 sine x minus 1? Yes, but if the axis of rotation were up here, we would have other bigger problems because the axis of rotation would then be going through this region. But if we didn't have that issue, right? If we didn't have the issue where the axis of rotation being up here kind of puts it through your region, then that would be correct. So if this was like minus 1/2, then these would be plus 1/2. If this is like minus 3, then these would be plus 3s. So a safe way to think of those is always as distances. Distance from the near end of the strip to the axis of rotation, and distance from the far end of the strip to the axis of rotation. Once we have these things, we know that dV, my little differential volume, is pi times big R squared minus little r squared times dx. That's the volume of this little washer here. And we're gonna have to plug these guys in and then integrate dV. And we're gonna have to integrate from x equals 0 over here, because this is where my like leftmost strip is, up to x equals pi over 4. So my volume, the integral from 0 to pi over 4 of dV, which is pi, times the integral from 0 to 4 of big R squared is 3 cos x plus 1 squared minus little r squared, which is 3 sine x plus 1 squared all times dx. No, good question. The axis of rotation, well, only in a few very special circumstances can we handle the cases where the axis of rotation actually cuts through the region. And the way we handle it in those circumstances is by making a symmetry argument and getting it out. So in general, no, you do not need to worry about how to handle these problems where the axis of rotation kind of plows right through your shaded region. That should not happen for these. Except in the case where you're looking at something that's perfectly symmetric, like above and below the axis of rotation, and then you can just ignore one of them. So think like a sphere, right? Like you can take the unit circle and revolve it around the x-axis to get a sphere. There, your axis of rotation would cut right through your region. But then you realize that you don't need the bottom half of the unit circle to get that sphere. You can just throw that part away and revolve the upper semicircle about the x-axis, and that'll give you the same unit sphere. So no, in general, you should not have to worry about the axis of rotation going through your region. All right, how do I do this integral? Oh, this is a pi over 4. I'll just wrote the 4, pi over 4 here for my upper bound. That's correct here. I'm going to switch back to black now because this black pen writes a little better. Here's the pi, integral 0 to pi over 4. We need to FOIL all this stuff out. So this is 9 cos squared x plus 6 cos x plus 1. And then we're going to FOIL and subtract all of these. So this will be minus 9 sine squared x minus 6 sine x minus 1 dx. The ones go away. The 6 cos x and 6 sin x are easy enough to manage. What about the 9 cos squared minus 9 sine squared? I see two ways to manage the harder parts of this integral. Let me show you a slick trick here. This is an opportunity to use an identity we don't use a lot. So the ones cancel, and I put the cos squareds and sine squareds together, put the coses and sines together. And sort of the standard way we would jump in here, we would integrate each of these separately, right? Sine squared and cos squared. We would use a half angle identity on each of these. Rewrite this as 1/2 times 1 plus cos 2x. Rewrite this as 1/2 1 minus cos 2x. What you'll see here is that cos squared minus sine squared cleans up very nicely. Half angles on these. This for this guy, this for this guy. And when you do that, what you'll see is that the cos squared minus sine squared, everything here is going to simplify really nicely to just cos 2x. So this is pi integral 0 to pi over 4, 9 times the cosine of 2x. That's what this little parentheses piece is cosine 2x. Plus 6 times this piece, there's nothing magic like that. We can do cos x minus sine x dx. We just got to deal with it. Okay, and now our antiderivative is easy. So at this stage, I know how to take the antiderivative of everything in here. Cosine of 2x, that antiderivative is sine 2x over 2, or 1/2 sine 2x. I'll write this as 9/2 sine 2x plus the antiderivative for cosine, so plus 6 times antiderivative for cosine is sine. Antiderivative for sine is negative cosine, so this will become a plus cos x. And all this is evaluated from 0 to pi over 4. So the cos 2x piece is like a little micro u sub. All right, the tiny, tiny u sub you need to integrate this is u equals 2x. du is 2 dx, so you get a 1/2 out. That's the 2 here. And then you're just integrating cos u du, which would be sine u, which would be sine 2x. There's no need to write all that stuff out, right? Way back in the day, we said we should be able to do integrals like cos ax and sine ax very quickly. And we can. They're not. And then, of course, each of these, those are just basic known antiderivatives. Let's see, what do I get if I evaluate this at 0? Do I get something? This piece is 0, this piece is 0, this piece gives me something. Okay, we'll just go through it then. So at the upper bound, give myself a little more space. When I plug in pi over 4, we'll have 9/2 times the sine of 2 times pi over 4, which is 9/2 times the sine of pi over 2, then plus 6 times sine pi over 4 cos pi over 4. Yeah, like it's not hot.
No, it's fucking awesome.
Very nice. Okay, so here's what we get when we plug in our upper bound. And then minus what we get when we plug in our lower bound. We'll have 9/2 times the sine of 0 plus 6 times sine of 0 plus cos of 0. All right, lots of trig to evaluate here. Let's start on this end. What is the cosine of 0?
One.
Good. What is the sine of 0?
0.
Very good. So both 0. What is the cosine of pi over 4?
Radical 2 over 2.
Very good. Root 2 over 2 or 1 over root 2. And that's the same as the sine of pi over 4. What's the sine of pi over 2?
1.
Very good. All right. So out from this big mess, we get 9/2 from this piece plus 6 times root 2 over 2 plus root 2 over 2. So I'll write it like that. Why not? And then minus 0 times 6, sorry, 0 plus 6 times 0 plus 1. This is just minus 6. One of these pieces can be cleaned up mightily, or at least a bit. This, right, root 2 over 2 plus root 2 over 2 is 2 times root 2 over 2, which is just root 2. So this whole piece is 6 times the square root of 2. 6 as a ratio over 2 is 12/2. 12 minus 9, I'm sorry, 9 minus 12 is negative 3. This is negative 3/2 plus 6 times the square root of 2.
I think you left out the constant of pi since the second step.
Yes, thank you, thank you, thank you. Yes. What are you talking about? It's right here. You're absolutely right. Yeah, we have a factor of pi that I forgot to carry from that previous step. Yeah, so pi times negative 3/2 plus 6 root 2. All right. Questions on this? Any part we want to look at a little more closely?
Could you please go up to see one of the steps you did in the first page?
Yeah, there was a private message request about how this stuff became this stuff. Is that what you wanted to look at also?
Yes.
All right. So one thing, let me flip this page over so we can annotate a little bit. So one of our identities, if you look back on that day where I gave you like a list of identities, one of them is just straight up cos squared x minus sine squared x is cos 2x. This is the double angle identity for cosine. So when I see this, I don't even think to go through these steps. I just go, oh, that's cos 2x, like straight up. But you could also get there as by way of these half angle identities. So if you forgot the identity at the top, you can combine the two at the bottom. These two as a pair imply that cos squared x minus sine squared x is equal to 1/2 times 1 plus cos 2x minus 1/2 times 1 minus cos 2x. And if you distribute everything, this is 1/2 plus 1/2 cos 2x minus 1/2 plus 1/2 cos 2x. The 1/2s cancel, and you get 2 times 1/2 cos 2x, which is just cos 2x. So if you happen to have forgotten that double angle identity for cosine, you can cook it up. Let me hold here for a second for those who are wondering about this, and then I'll address the other question that was asked. So I think it is worthwhile having this in your head, right? You should know a half angle identity for sine and a half angle identity for cosine. You should know a double angle identity for cosine and a double angle identity for sine. While we're here, the double angle for sine is 2 sine x cos x. This is sine 2x. And we have to use this in the trig subsection quite a bit. So these are your double angle identities. And there's like 2 other versions of the cosine double angle identity, but this is the one that I hold on to. And then these are your half angle identities. We definitely need those in addition to the Pythagorean ones. All right. The other question was about the radii. So before I go back and show you exactly where those came from, remember with the disk washer method, where your strip is always perpendicular to the axis of rotation. Kind of the whole story there is that dv is pi times the outer radius squared minus the inner radius squared times either dx or dy, we'll call it dt, where big R is the distance from the far end of the strip to the axis of rotation. And little r is the distance from the near end of the strip to the axis of rotation. All right, so this is our guiding principle, right? This is pretty much everything you need to know about the disk washer method to make shit work. And we gave this, right? We had a day where we outlined kind of a neat characterization of each. So the question was, how did we find big R and little r? We come up here in our nice drawing, right? Make sure you draw your region nice and big. Give yourself lots of space to get in here and label things. Here's my strip. Here's my axis of rotation. So little r should be the distance, right? The strip has an end that is closer to the axis of rotation and an end that is further from the axis of rotation. The width of this strip is thought to be like infinitely narrow. It's differential. So like horizontally, we think of this strip as having a very, very, very narrow width, basically width 0. So you don't need to worry about the width much, but you do need to worry about these distances. So the near end of the strip to the axis of rotation, that's little r. So that's this. So first we label it in the picture. And big R is the distance from the far end of the strip up here down to the axis of rotation. So this is big R. Remember the strip is always in here at what we call a generic X value or generic Y value. So we're asking like, what is, for big R, we're asking what is the distance from this end of the strip to the axis of rotation? Well, this point up here, along the curve y equals 3 cos x is x comma 3 cos x. So if we want to find this distance, which I know is big R, I take the y value up here and I subtract from it the y value down here. The y value up here is 3 cos x because I'm along the curve y equals 3 cos x, right? That's that boundary curve. So the y value here is 3 times cos x. The y value here is -1. So that radius is 3 cos x minus -1, which is +1. And the same sort of thing for the inner radius. This point right here is x comma 3 sine x. Because we're along the curve y equals 3 sine x there. So what is this little distance here? Well, it's the y value at the top, this thing, minus the y value at the bottom, this thing. So that's 3 sine x minus -1, or 3 sine x plus 1. Does that help with the radii? Yeah, let's come back to this. So if you go back to the last day we spent in 6.2, I think that's where I laid this all out for the first time. Yeah, here, this is basically our full characterization of the disk washer method. Now here, dt can be dx or dy. It's either dx or dy, depending on the situation. So if your strip is vertical, then it's going to be a dx. If your strip is horizontal, it's going to be a dy. Anything else about this that we want to look at?
Could you go back down to the second part of what you did?
Yeah. Oh, the antiderivative step? Sure. Yeah, let's do that. Where did that? So after we rewrite cos squared minus sine squared as cos 2x, all the antiderivatives are very easy. The only one that requires any real thought is this guy. So maybe if there's one thing I would say to remember there, do this in that same color. I'm going to leave off the constants. The integral of cos ax dx is 1 over a times the sine of ax, or sine ax over a. And the integral of sine ax dx is -1 over a cos ax. These are like micro use ofs. right? They're U subs so small you don't even need to do them. You can see exactly what's going to happen because you've practiced U sub a lot. Okay, I feel like we've spent enough time on this problem. If there's anything else that's burning here you really want to talk about, come see me in office hours, we can do that. Let's move to the other question because homework 5, number 3. We can look at a work problem. Yeah, the work problem, I don't know if you guys have noticed this yet. The work problem in your study guide is actually a bit harder than I intended it to be. I did not solve that problem ahead of time and I didn't realize exactly how challenging it is. So if you get a little strung up on that work problem, don't feel too bad. We can look at that next, but let's do homework 5, number 3 first. Okay, we want to evaluate this integral. Just 1 minute to write it down. Okay, kindly, they have already factored the downstairs for us. They've already factored the denominator for us. We see the denominator of this expression would be a degree 3 polynomial if we multiplied everything out, and the numerator is a degree 2 polynomial. So this is a proper rational function. The integrand so we're thinking partial fractions. Right, unless there's some magic substitution we can make that cleans this all up, which I don't see. We're going to need some partial fractions here. All right, what does that partial fractions setup look like? So we're going to run partial fractions. That setup is x squared plus x plus 1 over x plus 1 squared times x plus 2 equals. How many terms are there going to be altogether in this PFD setup? Let me ask that qualitative question first. How many terms?
3.
3, good. 2 from the x plus 1, 1 from the x plus 2. So the x plus 1 squared, that's a repeated linear factor. So that's going to get a over x plus 1 plus b over x plus 1 squared. Both of those coming from this guy. And then I'd have plus c over x plus 2. That is the correct PFD setup here. So remember, if you have a repeated linear factor, you've got to build up to that multiplicity. If this was a x plus 1 cubed, I would do a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed, and then plus d over x plus 2. My next step is to clear out those denominators. My left-hand side will just be x squared plus x plus 1. And on my right-hand side, when I multiply everything over here by x plus 1 squared times x plus 2, one of the x plus 1s will cancel here, and I'll have a times the other x plus 1 times x plus 2. Plus, when I multiply this guy by x plus 1 squared times x plus 2, I'll just get b times x plus 2. Both of the x plus 1s cancel. And when I multiply this guy by x plus 1 squared times x plus 2, the x plus 2s cancel, and I just get c times x plus 1 squared. And in this line, I can use my Heaviside trick. I won't be able to get everything, but I'll be able to get a lot. What sort of x values should I plug in? I should send x to where if I want to get information out of this line?
-2,
Good, -2 and
-1.
very good, right? The two values that make these factors 0. So as x goes to -2, we have on the left-hand side, -2 squared plus -2 plus 1 equals, what survives on the right-hand side? Well, this term, when x is -2, is 0, so this whole thing goes away. Similarly, this term, when x equals -2, is 0, so this whole thing goes away. So the only term that makes it out alive is this guy. It's c times -2 plus 1 squared, which is -1 squared. So what is this? This is 4 minus 2 plus 1, right? 4 minus 2 is 2, plus 1 is 3. C times -1 squared. Well, -1 squared is 1. So that gives us C right away. The other value we need to look at for the Heaviside trick is -1. We must send x to -1. So there I'll have on my left-hand side -1 squared plus -1 plus 1 equals. And now all the terms on the right that have an x plus 1 will disappear. So this term, this is going to be 0, so this whole thing goes away. This term, this piece is going to be 0, so this whole thing goes away. And -1 plus 2 is +1, so my right-hand side here is just b times +1, which is very nice. On the left-hand side, as we clean this up, I've got -1 squared, which is 1, -1, which is 0, plus 1, which is 1. So b is just 1. I've got b and c. There is no nice way to get a. Right? We cannot get a out for free using the Heaviside trick. But I can plug these numbers in. I can plug b equals 1 and c equals 3 into this equation here, which we sort of in the habit of calling star, to get a new equation. X squared plus x plus 1 equals a x plus 1 x plus 2 plus just 1 times x plus 2 plus 3 times x plus 1 all squared. And now I can multiply things out and collect like terms. This is x squared plus x plus 1 equals, let's look for our quadratics. I'd have ax squared from this, and 3x squared from that. And I don't really care about anything else because this is plenty for me to get the job done, but I'll go ahead and write out the other terms. So here I would have plus 2x plus 1x is plus 3x, so I'd have plus 3a times 1, oh, sorry, plus 1x here, and filling this out, this would be x squared plus 2x plus 1, so that's plus 6, so plus 1 plus 1 from this, and plus 6 from this, it's plus 7 x. All right. Oh, I'm not taking, did I take this into account too? Sorry. So we say plus 1x plus 2x plus 3x, good. 3a there. A plus 1 plus 6. Yeah, that's good. And then my constant terms. Here I would have 2, so 2a have 2, and here I have 3, so plus 5. But we can just use the first one of these. We've got 1x squared equals a plus 3x squared. So a plus 3 has to be equal to 1. Which means a has to be 1 minus 3 is negative 2. And you can check that these work for the others. You plug negative 2 in for a here, then this would become negative 6. Negative 6 plus 7 is positive 1x, good. If you plug negative 2 in here, then this is negative 4 plus 5, which is also 1. Okay, good. Are we all clear on where I'm getting A, B, and C from here? Everything in the squiggly bracket is the Heaviside trick. And then after we get everything out we can with the Heaviside trick, we have no choice but to go back to the equating coefficients business, but we can plug the values in that we found. And that makes our life a little easier. So my function is equal to a over x plus 1, that's negative 2 over x plus 1, plus b over x plus 1 squared, that's plus 1 over x plus 1 squared, plus c, which is 3 over x plus 2. Which means the integral from 0 to 2 of this guy dx is equal to the integral from 0 to 2 of this guy dx. And now each of those terms on the right-hand side is quite manageable. You need little substitutions. Well, I'll go ahead and write it out, why not? So that's negative 2 integral 0 to 2, 1 over x plus 1 dx plus integral 0 to 2, 1 over x plus 1 squared dx plus 3 integral 0 to 2, 1 x plus 2 dx. Each of these get handled a little differently. In the first guy, I would substitute u equals x plus 1. And this would become 1 over u du because du is just dx. So again, kind of little micro u sub. This is negative 2 times the natural log of the absolute value of x plus 1. And he's going to get evaluated from 0 to 2. Plus. This middle guy, if you sub like v equals x plus 1 here, dv would again be dx, so the differential doesn't change anything. It's another one of those micro u subs. And you'd have integral 1 over v squared, which is negative 1 over v. So this piece is going to be minus 1 over x plus 1, evaluated from 0 to 2. And the last guy is also going to be a natural log. Right? If you sub w equals x plus 2 in this integral, dw is dx, and you get 1 over w dw. So this is going to be plus 3 times the natural log of the absolute value of x plus 2, evaluated from 0 to 2.
When we do those micro u subs, do we not have to change the bounds?
It's a good question, right? So what I'm doing is I'm saying I can figure out the antiderivative for this thing in my head. That's kind of what I mean by micro u sub. If I wanted to rewrite this integral in terms of the new variable, like actually write out the substitution, then you should change the bounds. But if you can do the kind of U sub process to get your antiderivative in your head without making mistakes, then you can keep everything in terms of X. So because I never actually made a substitution, I never actually wrote down U, V, or W, I didn't have to change my bounds. But if I did, if I wanted to write this as integral 1 over U du, then that would have to be from 1 to 3 rather than from 0 to 2. Yeah, the details on the middle integral. Here, imagine letting W equal X plus 1. Let me, I'll write it out. Explanation page, right? So I have integral 0 to 2, 1 over X plus 1 squared dx. If I wanted to do this carefully, I'm actually going to write out the substitution where I plug everything in, then I do need to change the bounds. So my old bounds were X equals 0 and X equals 2. When X is 0, W is 1. When X is 2, W is 3. So if I'm writing this out, this would become integral 1 to 3, 1 over W squared dW, which is integral 1 to 3, W to the negative 2 dW, which is W to the negative 1 over negative 1 from 1 to 3, which is negative 1 over W. So if we wanted to do this carefully, we could do it like this. And this would be negative 1/3 plus 1, which is what we're going to get when we evaluate that other piece. Now, what I'm doing in my head, so carefully, I said, okay, I'm just going to pretend like this is the indefinite integral 1 over X plus 1 squared dx, because I think I can do this in my head. The kind of substitution there would be like V equals X plus 1, same thing, dV equals dx, but I pretend like it's an indefinite integral. So this becomes integral 1 over V squared dV, which I know is V to the negative 1 over negative 1, which I know is negative 1 over V, which I know is negative 1 over X plus 1. So since it's pretty easy to go through each of these steps in your head without writing anything down, I can conclude what my antiderivative should be without going through any of those kind of procedures. The minus I put out here. So I would say if you can do this in your head, then you can jump here to here and not worry about changing bounds. If you're uncomfortable doing that much stuff in your head, which is totally understandable, this is how you do it carefully. If you're going to write out the substitution and actually write the substituted integral, you do need to change the bounds. But if you can just jump straight to the antiderivative, then this is okay. So those are good questions. Any other questions so far? All right, and we're doing the same sort of thing here and here. It's just that there's no power. So this would become like 1 over U, and this would become like 1 over Z. The last move is just to evaluate. I don't think the evaluation here would give anybody a hard time, but we can look-see. So at the upper bound here, give myself some space, I have -2 times. At the upper bound here, this is the natural log of 2 plus 1, which is the natural log of 3. Minus, at 0, we have the natural log of 1. Minus this thing, at 2, we have 1/3. And then at 0, we have 1 plus 3 times the 2, we have 4 minus the ln of 2. The natural log of 1 is 0. You got to know that shit. So this is negative 2 ln 3. 1/3 minus 1, this is 1/3 minus 3/3 is negative 2/3. With a negative here makes positive 2/3. And then 3 ln 4 minus 3 ln 2. Not much to do there. It is possible to combine all these logarithms together, but I don't mind if you don't. Okay. Hold here just for a second because we've got pretty much the whole problem visible. I'm just talking to myself. Left in the class. Okay, the other thing we wanted to look at was a work problem. Was there a specific work problem?
No specific one, just maybe one, like the one from the study guide, or a simpler one that would be similar to something on the test.
So first, let me give you a little hint on the one from the study guide. There. This is homework 5. Yeah, the study guide one is actually more challenging. I forget who it was. Somebody came by office hours yesterday with it, and I was like, oh wait, this is no, this is not easy. Okay, what do we do? So 7. And 1 joule. 5. Stretch from 9 cm to 11 cm. All right, so here's the problem as it's stated. The first thing I would do is convert everything to SI units. So joules, those are already in SI units. Those are Newton meters, but centimeters are not SI units. And this is 1 joule here. So 7 centimeters is 0.07 meters. 0.09 meters. 9 centimeters is again 0.09 meters, and 11 centimeters is 0.11 meters. Here's the picture. See, the thing is, normally we have a slightly different set of information. Normally we're told like some bit of information that'll let us solve for the spring constant K, and then asked to answer a question about work. So remember Hooke's law says that the force required to hold a spring at a certain distance, X, is proportional to that distance. So this is your force to hold. And X here is the distance stretched or compressed from the natural length. We weren't given the natural length here, right? They said find the natural length. That's our goal. So what I would do is I would kind of draw the system. And let me call this the natural length, n. Sorry for my shitty spring, but there's our spring. We know that to stretch it from 7 centimeters to 9 centimeters required 0.6 joules. Let me just assume here's 0.07 meters. Here's 0.09 meters. So I know that to stretch it from here to here, right? If I bring this all the way out here and I start here, to stretch it from there to there is going to require 0.6 joules. So then the question is how far, like where we're stretching from where to where, what's that integral? And the challenge is to get it in terms of n. So 0.6 joules is equal to the integral of kx, that's your force, dx, but done from where to where? It's not from 0.7 to 0.9, which is what you might think. Because if you were to integrate from 0.7 to 0.9, you would be assuming those are the x values, which they're not. Remember, x is the distance from the natural length. So really, we would be integrating from where to where? To go from here to here, if the origin is over here, then we're stretching how far from the natural length?
0.07 minus n.
Very good. From here to here. Point 0.09. And this might feel a little bit weird, but just remember, x is the distance from the natural length. So if my origin is over here, if I'm calling this position 0, calling this position the natural length, then to go from here to here, my x values, my distance from the natural length is 0.7 minus n to 0.09 minus n. And this is an integral we can crunch out. The k pops out. You get a 1/2 x squared that you then need to evaluate from 0.7 minus n to 0.09 minus n. And I'll be 100% honest with you guys, I didn't see this at first, right? Worked this with someone in office hours yesterday. It took me quite a while, but this works. You can evaluate this. This is k over 2 times 0.09 minus n squared minus 0.07 minus n squared. And you know all of this is equal to 0.06 joules. So k is equal to, let's see, 0.6 times 2 divided by this. This lets me write k in terms of n. Now, if you take that second bit of information, that 1 joule is required to stretch from 0.9 to 0.11, same sort of thing here. This is 0.7 minus n to 0.09 minus n of kx dx, and you plug this k in here. So 2 times 0.6 is 1.2. for 0.09 minus n squared minus 0.7 minus n squared. What's this? Sorry. This should be 0.09 to 0.11. So that's your k. Well, this times x dx. I won't spoil it for you. The rest you can do on your own. But this is the big step, is realizing to set the bounds like these. Solve for k in the first guy, then plug into the second guy. So all of this is equal to 1. And then you crunch this integral out, and you'll have an equation you can solve for n. It's really not that bad. 1 equals 2 divided by 0.09 minus n squared minus 0.07 minus n squared times x squared over 2. All right, sweetie. Oh, I need to change both of these. Sorry, I didn't change that one. So this is from 0.09 minus n to 0.01 minus n. When you plug these in, you'll get some terms that look a lot like this, only with 0.11 and 0.09. Solve the resulting equation for n. It's a quadratic. It's a big quadratic. And n, remember, is the natural length. That's the thing you're after. This is a harder problem than I would put on a test. I think the setup is quite hard, and then the calculation steps are somewhat involved. So I can show you a quick example of a problem that is closer to what we would see on a test. The next step would be to evaluate and solve. Yeah. Something a little more like what I could ask you on the test itself. So 7, 8. 9. These are all good. In fact, I think 9 is a nice example here. Unfortunately, we were about out of time. So I'd say if you want looking for work problems that you could practice that are a little bit closer to the difficulty of the problems on the test, I would say any of these 7, 8, or 9 would be a good place to start. Alrighty. So unfortunately, I don't have time to go through these, but each of these are very similar to the ones that were in your homework back when we covered this section. First bit of information lets you find k. Second bit of information tells you how to set up your integral. They're not bad. I promise. If I put a work problem on the test, it will be very gentle. It'll either be like a qualitative question, like does the time factor in, like this, or it'll be a really simple spring problem. All right, you guys, I got to get running, so I got another class that starts at 11. If you do want to talk anymore, I have an office hour this afternoon from 1 to 2 p.m. Otherwise, you can send me a Canvas message or reach out on Discord. What else do I want to say? Oh, the testing center, right? I've had a few people reach out to me and say they want to take the test at the testing center. Testing center got a little grumpy with me because I sent a bunch of people to them this week without realizing that they lost a lot of folks lately. So they only have like 2 staff on at any given time. And they're really not in a position to handle large groups right now. So if you want to take the test at the testing center, it's okay. Let me know and I will make a reservation for you. But we unfortunately can't send everybody there. So if you're able to take the test online, it's not going to cause you a headache, like it doesn't cause you scheduling issues or whatever. Then I would probably prefer you take the test online with me here in Zoom. But if you're unable to do that, or it would be a real hardship for you for any reason, then I'm happy to move you to the testing center. So anybody who's already asked to go to the testing center, I've already made your reservations, you're good. And I just wanted to share that with you. They've got some updated rules there too, like you guys aren't allowed to scan your own work in the testing center because some people are being shady with their cell phones and doing sketchy shit. So they will collect your work and I will go get that physical piece of paper from them after the fact. All right, any last minute burning questions here? Okay, I would invite you guys to try and find a nicer solution to this problem. So if you feel so inclined, especially if you're into physics, I have a feeling there's a nicer way to do this. Probably has to do with changing your coordinate system, like setting this as 0, which is kind of what we normally do in these problems, setting the natural length to 0. But yeah, I'd be curious if anybody comes up with a different solution than this. All right, I got to get running. If you want to talk, come by office hours, send me a canvas message, Discord. If you've got an extension request in WebAssign waiting, it'll be cleared later today. I cleared everything yesterday, but I'm just getting tons of them constantly. So watch in the near future. That's it from me, guys. Remember, submit your study guides as soon as you can. That way I can go in there on Sunday and give you some feedback on them. Oh, that's okay. Yeah. So if you've already sent me a message saying you want to take the test at the testing center, you're good, right? All of those people, you already have reservations. You don't need to worry. I'm just saying that in case anybody is like on the fence or trying to decide if they want to. If you don't need to, then it would be preferable to take it online just because they're short staffed right now. But that's it from me, gang. I will see you all next time. Keyboard failing? No, there we go. All right. Take care, gang.